In this graphical method, we can find the order through how the curve or how the data form, when we make the graph. Okay, in this graphical representations, there are two types of graph: the concentrations with time and the rate with concentration. In the zero order region, if you increase the concentration, if you increase the concentration, then it will decreases. It will decreases with time, because the reactions will use the concentrations of reagent. Okay, but how the concentration of reagent affect to the rate of reaction? It does not affect at all. So if you increase this to this, the rate will be stay here. Increase more, the rate will be stay here. So will not affect. So this is the zero order reaction. So will be expressed by rate equals to K times A to the power of 0. And this is 1. So rate equals to K. The rate of reactions just depends on the rate constant value. Okay. This is the graph of the first order ratios. The concentration will be decreased with time, and make the curve graph like this. And if you plot the data, the rate of reactions with the concentration, and the graph will be like this. Okay, so please remember the zero order of concentration with time like this. Then the first order will be like this. Before. And for the rate with concentration, for the zero order like this, for first order like this, directly proportional. Okay, so the slope here is negative K. For this slope is K. The slope is K. We have learned the first order reactions graph in the previous videos. Okay, this is the second order graph. In the second order graph, you can see that it has the similar shape with the first order, but will be lower like this. Concentration with time will be decreased more compared than the first order. And for the rate with concentration will be like this. You can see like this. It's parabola. Parabola. Okay, so if you plot the data and then you get one of these type of curves, then you can find the order of reaction. Okay, this is the summary. The zero order, first and second. Okay, like this. Okay, but some of students will ask about why we can produce this type of graph, right? Why the zero order have this type of graph? We should memorize, or is there any explanation of why the first order reaction, for example, produced this type of graph? Yes, there is another explanation. We call this as integrated rate law. In integrated rate law, later on I will explain about how to derive this. The zero order, first order, and the second order produce the formula. The integrated rate law for zero order will be like this. Concentration A is equals to negative Kp plus concentration A at time 0, the initial concentration. For first order will be like this. Ln A, ln concentration of A, negative Kp plus ln concentrations of initial A. And for the second order will be like this. Okay, you can see from this table as well that y in the first order reactions, you can find that the t half is equals to 0.693 over k. You should already see this formula in the second video, right? So because we need to understand about why this this zero first and second order produce this type of graph. So I like to introduce the integrated rate law to all of you. I will use the whiteboard now. Okay, in the integrated rate law, you should remember about the integral rules. Okay, so for example, if I have integral of dx, this will be same as this will be result x plus c. Okay, in a definite integral, I will give the upper bound and the lower bound. So for example, if I have dx, for example, this is let me think, this is x0 and x. So this will be x to x0. Okay, will be like this. This is the definite integral. Okay, let's see another example. Integral of x to the power of negative 1 dx. This is same as dx over x, right? Integral of dx over x. This is ln x. Okay, ln x. Okay, please remember about this integral rules. Okay, and then one more is, for example, if I have x to the power of negative 2 dx, this will be produce x negative 2 plus 1 over negative 2 plus 1 plus 3. Okay, so this will be produce x to the power of negative 1 over negative 1. So this will be negative x to the power of negative 1. Okay, so you should understand about the integral rules first. Okay, because we will need this the integral rules to solve the order of regions graph. Okay, now let's start with the zero order. For example, I have reaction A to form B, and this is zero order to A. Okay, as you know, that rate of reactions can be expressed as the decrease in concentrations of A. Okay, rate of reaction can be expressed as the decreased concentrations of A. That means I will give negative sign here. Need negative concentrations of A over time, or it can be expressed as well in the rate of equation like this. Rate equals to K times concentration A to the power of 0, right? So we can combine these two definitions, yeah, in the integration form. Okay, negative delta concentrations in mathematics, yeah, is better for us to make in the differential form. Okay, so negative D concentration of A over dt equals to K times concentration A to the power of 0, which is 1. Yeah. So negative dA, the concentration A over dt equals to K. Okay. And then we can shift we can move the dt to the other side. Yeah, because of we cannot integrate this. So we should move this to k dt. Okay, and then next we can integrate this negative integral of dA equals to k integral of dt. Okay, now I'd like to give the upper and the lower bound. Okay, since this is the definite integral from the initial concentration to concentrations of A at time t, okay, at a particular t. So we call this as the lower bound is A0 and the upper bound is A. Okay, and then for the t from the time 0 until the time t. Okay, so back here, that if we have the integral of dx is x plus c. Okay, so for integral of dA, this means we'll produce the negative concentration of A, yeah, with the bound, yeah, concentration A with concentration of A0 here. And this will be same as K times T minus 0. Okay, now let's continue. So negative concentration of A minus negative of concentration A0 equals to KT, or concentrations of A0 negative minus concentrations of A is equals to KT. So concentrations of A, I move to the right side. So concentration A is equals to concentrations of A0 minus KT. So if we assume this is we want to form a graph, yeah, so we can assume this as Y. Okay, and this is C, and the K is the slope, which is M, and this is X. Okay, the slope is negative K. Okay, so now I'd like to draw the graph between the concentration of A with time. Okay, let's assume if t equals to 0, yeah, if t equals to 0, here this is 0, minus kt, that means 0. So A equals to initial A0, this. So at T0, yeah, the concentrations of A equals to the initial concentration. Would be like this. Okay. If concentration A equals to 0, if A is 0 here, this is 0, then KT equals to A0, right? So T equals to concentration A0 over K. Okay, so concentrations A will be 0 at time concentration of A0 over the rate constant. So we can make the slope like this. Okay, so the slope is my negative K. So that's why in the first order, in the zero order reaction, the graph of concentrations versus T will produce this shape. Okay, we produce this shape. We need to make the another graph, which is the rate of reaction over versus the concentration. I mean, okay, to make this graph, you just need to see this formula. dA over dt is rate, right? This is rate. And we can ignore the negative value, okay, since the negative is just show that this is decrease. But if you want to find the rate of region, we can ignore the negative sign. Okay, so because of dA over dt, or the rate of regions, only depends on the value of k, and the k is the number, yeah, a certain number, for example here. So will produce this type of graph, yeah, just a horizontal line like this. That means if you increase the temperature, the concentration, if you increase the concentration, the rate of reactions will not change, at all. Okay, so that's why now we already see that why the zero order reactions produce this type of graph and this type of graph. Okay, understand? Okay, you can pause this video if you want to um take notes regarding of how this graph produced. Okay, now let's continue with the first order reaction. Okay, in the first order reaction, the change of concentrations of A over time, yeah, equals to K times concentrations of A to the power of 1. Okay, so dA over dt equals to negative K yeah, times A, concentrations of A. I'd like to combine A with A, so dA over concentrations of A equals to negative K times dt. And then integral of dA over A equals to negative K integral of dt from 0 to t, and this from initial concentrations to A, yeah, at a particular time. Okay, now let's see the integral rules once again. So if we have this, dx over x is equals to ln x, right? So that's why we can use this rule, yeah, to find out that dA over A, integral of dA over A is equals to ln A with this one. Okay, and then this is same as K times T negative minus 0. So ln concentrations of A minus ln concentrations of A0 equals to negative KT. This is same as logarithm ln A over concentration of A0 equals to negative KT. Okay. So if you want to find the graph of concentration versus time, you should find the A over A0 without the ln. Okay, so to convert ln to this, you should use the epsilon to the power of negative KT. Okay, so concentration A will be equals as concentration is 0 times epsilon negative KT. Now let's make the graph. This is concentration A, this is time. If T equals to 0, then epsilon 0 to the power of 0 equals to 1. Okay, So because this is equals to 1, then concentration of A equals to concentration of A0. Okay, so we have this point. Okay, at T0, concentration of A equals to concentration equals to the initial concentration. How about if T like this? So epsilon to the power of this is equals to 0, infinite. Yeah. So concentration of A will be equals as 0 because the epsilon value is 0. So concentrations of A will be 0. So the concentrations A will be 0 if the time is infinite. So will be like this. Yeah. So this is the first order ratios graph between concentrations and time. So that's why the shapes of curve will be like this. How about if you want to make the linear graph? How to find the linear graph? I will erase this. Okay, for the linear graph, I will use this formula. Okay, I will write again here. Ln concentrations of A equals to ln concentrations of A0 negative minus KT. Yeah, move to the right hand side. Okay, this equals to Y. This is C. This is M. This is X. So this is ln concentrations of A with time. Okay, so if T equals to 0, then ln A equals to ln A0, right? So this is the point. Okay, and if ln A is 0, that means KT equals to ln A0. Yeah, because if ln A is 0 here, then you move the KT here. So KT equals to ln A0. So T equals to ln A0 over K. Okay, so we can get when the ln A is equals to 0, then the time here is equals to ln concentrations of A0 over K. Then you get the best fit line like this, and this slope will be equals to negative K. Okay, now we'd like to see about how to derive the half-life. Yeah, through this equation. Okay, I will use this. Okay, ln A over ln A0 equals to negative KT. So wait, I will erase this. Once again, what is half-life? Half-life is the time when the concentrations of a substance fall to the half from its original value, right? So let's say I will write again here, A over A0 equals to negative KT. The T here is T half. So we expect that A will be half from the A0 in this situation. Half from the initial concentration, right? So you can see here that we can cancel the A0, the initial concentration, and this will be produced ln half equals to negative K times T half. Okay, Now use your calculator to find the value of ln half. It is negative 0.693 equals to negative k times t half. So that's why t half equals to 0.693 over k. Okay, you can see that we find this formula. Okay, are we finished with first order reaction? No, we're not finished yet. Okay, now we want to make the graph of rate of reaction versus the concentration. Okay, we want to make the graph of rate of reaction versus concentration. Once again, the rate of reaction can be write as dA over dt. Okay, we can use this formula. Okay, dA over dt equals to negative k times concentration of A. So once again, if you want to make the graph of rate over concentration versus concentration, the negative sign could be ignored. Okay, could be ignored since we just assume that it is decreased, but for the rate of reactions, we just calculate the value, not the sign. Okay, dA over dt equals to Ka. Okay, if K equals to 1 and concentration A equals to 1, okay, this is 1, so dA over dt would be 1. Okay, so if concentrations of A is 1, concentration, so the rate of reaction will be 1 as well. So we can plot here like this. So how if K equals to 1, because K is constant, right? And A now changes to 2. Concentration A equals to 2. So dA over dt, that means equals to K, which is 1 times 2. So dA over dt will be 2, right? So if the concentration of A is 2, dA over dt or the rate of reaction will be 2 as well. So we'll be continue and make this type of graph. Okay. So we are finished. We have finished to learn about the integrated rate law for the first order reaction, and this will be produced this type of graph: concentration A over T versus T. Okay, and ln concentrations A versus T will produce the linear graph, and the graph of dA over dt versus concentration, rate over concentration, rate versus concentration will produce this graph. Okay, so once again, this type of graph is the product of the integrated rate law actually. So we have finished with the first order. Now we'd like to continue with the second order reaction. Okay, for A change to D, for the second order reaction, negative dA over dt equals to K times concentrations A to the power of 2. Okay, because this is the second order. So dA over dt, oh, wait, we want to make the graph of concentration with time first, okay? Concentrations with time. So we should compare A with A. So dA with A square, concentration is A square, equals to negative sign, move here, minus K times dt. So integral of dA over A square Okay, like I said before, according to the rules of the integral rules, integral of dA over a square will be negative a to the power of 1 negative k times t minus 0. Okay, so this will be produce negative 1 over concentrations of A minus negative of concentration of A0. Okay, this will be same as negative KT. Okay, rearrange this formula. So concentrations of 1 over concentrations of A0 minus 1 over concentrations of A equals to negative KT. Okay, 1 over concentrations of A equals to, I will move here, I will move the negative KT to the left hand side. So positive KT. Okay, 1 over concentrations of A equals to 1 plus concentration of A0 KT over concentrations of A0, or concentrations of A equals to concentration of A0 over 1 plus like this. Okay, now let's make the graph. Concentrations of A with time. If at T0, okay, the concentrations of A will be D0, so equals to A0. So we have this point at T0, concentrations of A will be equals as concentrations of A0, initial concentration. Okay, if T indefinite, so concentrations of A equals to 0. Okay, so concentrations of A will be 0 if T this, so will not goes to the x-axis, which is time. Yeah, so the graph will be like this. Okay, how to make the linear plot of the graph? Because for example, if we want to find the slope, for example, okay, you can use this formula. Okay, 1 over A equals to 1 over A0 plus KT. So we can try to make the graph now. This is 1 over A. Okay, and this is time. So at A0, at T0, then the concentration of 1 over A will be equals of 1 over A0, right? So this is the point. This is the concentration, the 1 divided with the initial concentrations of A. And because as the time proceeds, the value of 1 over A will be increases, right? So the graph will be like this. Okay. So the linear plot of the second order reactions will be produced between the 1 over considerations of A versus time. Okay, now for the third graph, we would like to see about how the curve between the rate of reaction with the concentration. Okay, we want to make the rate of reaction with concentration. Once again, the rate of reaction can be symbolized by dA over dt. Okay, we can use this. Once again, you can ignore the negative sign for the rate versus time graph, because once again, we just need the value. Okay, so dA over dt, okay, equals to k times concentrations A squared. So if k equals to 1 and concentrations of A equals to 1 as well, so dA over dt will be 1 times 1 square, right? This is 1. Okay, so let's plot here. If A is 1, this should be 1. Okay, like this. Now, let's change A to 2. If A2, then dA over dt would be k, which is 1, times 2 square, which is 4. So if we increase the A to 2, will be like this, right? Okay, to 3, this will be until 9, right? Oh, very high, like this. So let's plot this. Okay, we can find that we already find that the rate versus concentrations for the second order reactions will give the hyperbole curve like this. Okay. Now we'd like to find the half-life. Yeah, the half-life of the second order reactions. Okay. Once again, half-life is when the concentrations change to the half from its original value. So we can find out using this formula. So 1 over A equals to 1 over A0 plus KT. Okay, you can see that 1 over A can be changed to 1 over half from A0, right? Like this. Okay. Shift this to the left hand side. So negative KT equals to right. I need more space. Next, negative KT equals to half A0 minus A0 over half A0 square equals to negative KT half. Yeah. Okay, next you can cancel this with the, oh, no, wait. Yeah, half A0 minus A0 equals to negative half A0 over half A0 square. Okay, negative cancel. Okay, so KT half equals to, we can also cancel half with half. So 1 over A0, right? So T half equals to 1 over A0 over K, or 1 over A0 times K. Okay, so this is how we find the half-life in the second order reaction. So T half equals to 1 over initial concentrations of A times the red constant. Okay, so we are done with the zero, first and the second order reaction. So I hope you understand of how uh, this curve produced, yeah, and you can understand the mathematical derivation. Okay, so this is the summary. Okay, once again, for the zero order, concentrations of A equals to negative Kp plus concentrations of A0. For first order, ln A equals to negative Kp plus ln A0. For the second order, 1 over A equals to Kt plus 1 over A0. Okay, this is the half-life value.